energy in the ultraviolet light breaks the molecules apart into atoms. When they react to form hydrogen chloride, the energy given out is released as the heat, light and sound of the explosion. Buses, trains, and the people who use them. Heat, light, sound, explosions, such as the controlled explosions that drive the engines of cars. Everything that happens depends on energy transfer. Remember, energy transfers from high levels to low levels, becoming less and less useful as it does. So finally, will everything eventually run down?
Isambard Kingdom Brunel was best known for his railways, and this was perhaps his most impressive construction, the Saltash Railway Bridge. But building it posed some major problems. Each of those spans weighs about 1,000 tons and is 150 metres long. They had to be built at ground level and then lifted into position. And also they had to be high enough so that large sailing ships could pass underneath. Now this is a model of one of the spans, and remember that in reality these spans are incredibly heavy. This was actually built on the bankside, just where we are now, and you have to imagine that this is the bank, the span's sitting on it. How on earth did Brunel lift the spans off and get them into position?
Well, yes, he'd got 1,000 tons here, about 150 metres so he had big iron barges built, and do what I do, he filled them with water, he pumped water into them.
Right.
So they were sitting a lot deeper in the water, floated them in under the span.
Oh, I see, yeah.
And then he pumped the water out.
Very clever.
Yep.
So they lifted up.
Yeah. But of course, in those days, they'd always choose water as a solution. Of course, they could use steam engines for pumping this, whereas we have to use these hand pumps.
Well, my end's coming up now. It's almost floating. How about yours?
Yes, it's just about coming up there now. In a moment, we'll be able to float it out, So
how did Brunel direct all this?
Well, just imagine it. It was a tremendous occasion with the great man himself standing there in the centre of the span. But it was absolute silence as he directed it, as if he was conducting a great orchestra. And they got semaphores and flags, all sorts of ways of getting messages to people, because there weren't any walkie-talkies in those days. It was a wonderful piece of organisation.
And then they pull them out on great ropes?
Yes, once they'd got it floating, out it came. It floated off the bank on the barges, and they could haul it out with Brunel directing the pulling on the ropes, so they could pull it out, lower this enormous span down onto the base of the towers, and then they could start to celebrate. They could make a noise again. But it must have been a wonderful sense of occasion that the Victorians had, a tremendous style that, in a lot of ways, I think we've lost.
Now, if you had to lift a really heavy weight a certain height, how would you go about it?
That's the task for these 170 or so young problem solvers on day 3 of their course at Brunel University.
This is the weight they've got to lift. Now, it's 56 kilograms, which is really quite heavy. It's almost as heavy as me, and I can't even budge it off the table. So in order to lift it, they've been given these materials. Some steel construction kit, including these strips, and the plates and nuts and bolts necessary to put it all together. Some fishing line, which, by the way, has only got a breaking strain of 25 kilograms. Remember, that's a lot less than that weight. Some pulleys and spindles and the plates necessary for mounting them. Some casters so they can move everything around. And, of course, the tools.
Now, the idea this time is for each group to come up with a design that can be given to another group to construct. But there's more to it than just designing a method of lifting.
We've got to lift it up out of a container, move it 30 centimetres and put it in another container. How are you going to fix that? That's what I mean.
Oh, you got bolts, haven't you?
Yes, but fixing it at an angle, it's going to be unstable. Well, you get the trolley, it depends what we might have. If we have an A-frame. Yes, that's it, yeah.
You've got the wire going up and over.
So that,
You've got the pulley system here, couple of pulley system here.
So this
some kind of
on that.
handle attachment which you actually pull, which goes through the pulley system and then pulls it up.
That's brilliant, yeah.
The cord we've only has a braking strain of only 25 kilograms, is it? And the thing we have to lift is 52. So we've got three pulleys to carry to split the strain.
What are you going to do with these plans, these sketches? These sketches all being sort of agglomerated into the one main
Drawing.
sketch plan which will be given to the people to manufacture.
Where do I get what from?
Communicating a design to a potential manufacturer isn't as easy as you might think.
Are you actually...
That's one, that's another, and that's another, but in the opposite, in that place.
Is that section?
Yeah, that's a...
Thank you.
It seems that most groups are planning to lift the concrete block with a pulley system.
And then have pulley. I mean, we're not doing pulley, are we?
Obviously, this group has a different idea.
Your 4 strings.
The 4 strings here.
2, 3, however you're going to tie that, that can be sorted out. And your 4 rollers, castles,
On the
spindle.
yes, on the spindle, going like that, coming out. So you have your 4 strings coming out. You have your lever here. Yes.
And it's all these are attached.
And they all attach there. And then you've got a much greater leverage than if you were doing it perpendicular. So you've got all this leverage here.
So it's either a lever or a pulley system. But are they sure the materials they're planning to use to do the lifting will take the strain?
How's that going to hang in midair?
That is going to support 52 kicks, isn't it? Hopefully. Well, it depends. The guy who said he knew about fishing said that they usually do underestimate the braking strain. It's usually higher.
And what about the design of the frame of the lifting device?
I want you to explain to me how the Dexian is going to...
Because there's one piece...
Bolted together. If you bolted them together,
Yeah.
and these plastic end pieces won't fit on the top here.
They don't have to because it's going to be covered.
It seems to have got quite a long way. Can you explain to me how it all works, lifting this heavy block?
It's conventional third angle drawing. All it is one drawing, or 3 drawings all in one. This is your plan. This is your side elevation, and this is your front elevation, as if you're looking at it from there.
There's been a time limit.
Well, I'll let you get on because time's running out.
That's right.
They've had just 2 hours for the design stage.
These are the 6 designs selected which show devices to lift a concrete block. Let's take a look at one of them in detail. This drawing shows the complete structure with measurements. Up here, we've got a detail which shows how the concrete block is attached to the lifting device. And over here, we've got a list of components and how much they're going to cost.
Now it's up to the groups to manufacture the various lifting devices that have been designed. Remember, each group has to work from another group's design, and they've got just 3 hours to do it in. The first problem is going to be understanding the design instructions.
You've just got your plans. What do you think of them?
Well, we're looking for a list of what we've got to buy.
Oh, I see. So really you don't understand what you need to start off with.
Well, we've got to sort of count all the measurements out that they didn't miss anything out.
What do you think of the plan as a whole?
It looks understandable.
That's a start.
More than ours was.
Wow, you think it's better than yours?
Oh, definitely.
They've also bodged up insofar as there's nothing to hold these from coming in.
Who chose this design? You're not looking really happy about your plan.
No, we're not.
Why? What do you think's wrong?
Haven't taken a lot of things into account.
Yeah, I mean, fair enough, they couldn't actually work with the materials.
They've told us to round off some of the materials. It's going to take us ages to file it down. They just haven't taken everything into account.
So it's a bit slap-happy.
Yeah.
You just have to make some modifications.
They haven't.
Modifications are allowed, but they'll be taken into account when the judges make the final assessment.
Well, they haven't put anything about actually lifting it. This is their pulley design, and all it is for attachment onto the block, which would be sort of in the middle, underneath the frame. So we don't know how we're going to actually sort of incorporate something else, modify this, so that we can actually lift it.
Well, let's hope those problems can get sorted out during the making.
Does this match the plan which you were given? Not quite.
We've made modifications.
Can you show me what modifications you've made? Which ones?
One of the things was we removed the collar from the top one because we found it was a bit too broad to go in there.
And on the design, there was stubble on these crossbars. There was another piece fitting around
made
there.
it a U shape.
But we thought we'd better leave that out because we would have used up more than we were permitted in the amounts of Dexion. So we've eliminated that. And we've also doubled this nylon cord for safety reasons, so if one snaps, there's always a backup one.
Sounds like a belt and braces policy.
Well, this looks as though it's reasonably complete now. How's it going to work?
Well, we can't sort of push it over the block, we have to sort of carry it.
Now, the design has to allow the block to be raised at least 15 centimetres vertically, but it must also provide a means of moving it horizontally a distance of 30 centimetres. This looks like a novel way of doing it.
Block like this underneath. The shackle goes right down here.
How did you find the design that you had before?
All the measurements too short, so we had to put legs on it.
So you had to modify it somewhat?
All of it.
Have you made any changes from what was on the original plan?
Well, quite a few. We did have a major problem. Once we'd actually sorted out the size, we found we did have these plates fitted on here, this spindle down here. But we were given a measurement, and from the ground up to the bottom of the actual shackle which holds on the block. And when we actually made it, but we discovered that we did not have enough height, because before it couldn't go up any higher than the metal bar was down here, and there wasn't enough height, you see. So we had to disband the idea of the metal block, which did weaken it a bit. So now we're hoping that the Dexion will actually support the weight from here, and we should just about make it now by centimetres.
Let's hope that'll do the trick.
Well, this looks fairly sturdy. How is it actually going to work?
Well, first of all, we shackle it onto here by taking this out, putting the shackle in there, and then slotting this through the shackle. So that's back on, and that there will hold the weight. And then pull on this. These are 3-stranded, each one taking 25 kilograms. So that's got a 300 kilogram braking strain, and it's only got a lift 50.
Right.
Pull on this until that comes right up and touches that.
Yeah.
Then you just twirl that round there to hold it there, push it to 30 centimetres and lower it down.
So you're literally going to push it bodily along like this. And now for the judging. Well, the first thing they've got to do is pay their bills. Theirs cost $320, which is very expensive.
The cost of making each design is an important factor in the judging. The cheaper, the better. For an expensive design, this one doesn't look too hopeful.
Thank you very much.
Never mind, at least it wasn't their design. They were only the manufacturers.
A relatively cheap one now, $204.
The first of the lever designs. Success! Oh dear, what a pity. Another inexpensive design on the lever principle. Oh dear, the same problem as before.
This one costs $256.
Safety's another important criterion. How safe is this one? Now, will the fishing line take the strain?
What's happening to the feet? not his feet. Can you see? But it's lifting.
It's looking good, but oh dear. It's the mountings for the casters that won't take the strain. That's going to make it very difficult to move the device along. They're succeeding. Now they have to lower the concrete block into the box. Well done.
The next lifting device cost $256 to build.
Here's another device using a block and tackle, but the method of moving the concrete block across from one box to the other is very different.
The next one's another expensive device, $318.
This one's looking good. Never mind, it was a good try.
The next group's device cost $188, which is not cheap, but it's not expensive either.
The supporting structure on this design uses an A-frame, but it's not so much the frame design that seems to be the problem. It's more the lack of strength in the fishing line. Or is it?
It's above there, isn't it? Yeah.
Another successful solution to a hefty problem. But what about that hefty problem facing Brunel, lifting those weighty spans of the Salt Ash Bridge into place? We know how he moved them away from the bank, but that was only half the problem.
So I suppose that once Brunel actually floated the span into position, he could then fill the barges up with water so they'd sink down, then the span would go down as well and rest on the base of the piers. In fact, the very piers that are behind us now, that's not much good as a bridge. I mean, you can't fit any ships underneath. How on earth did he get them up there?
Then he'd be using water again, Sue. You see, these are hydraulic jacks, this end and that end of the bridge, and he pumped water under pressure into them, like this, you see, so that they start to lift the bridge up.
It's lifting right off the base of the piers.
Yeah. And once he'd actually got it up about a metre, then they'd hold it up on the jacks, and then they would build masonry under the span to hold it. Would you like to put a block in under yours to simulate the masonry?
So they could support the bridge.
Right? You call this jacking and packing. And then once it's packed under safely, so they can take the pressure out of the jacks, the weight will take the cylinder down. Now we can lift the cylinder up. Can you do it the same your end?
Right.
So that,
oh, I see.
so you they lift the cylinder, and then they'd build masonry underneath that.
Underneath the jacks themselves?
Underneath the jacks. Is your end okay?
Yep.
No.
We'll start all over again.
And start all over again. Start pumping.
That must have taken a long time.
Well, it took them about a year.
Perhaps you can work out a quicker way of doing it.
An order form for the notes that accompany this series, then
apply heat to the iron until it's red hot. How hot? Well, you know you can measure hotness with a thermometer. But you can show hotness by using a thermographic camera. Watch this. So what is hotness? And why is it spreading out like this? Let's start again, but this time with the atoms. This model shows iron atoms in a piece of iron. They're always moving. They have kinetic energy. Hotness is a measure of the kinetic energy of atoms. We'll apply heat to the weld area. Some of the hotness is transferred to the iron atoms. As their kinetic energy increases, so does the temperature of the metal. In the area of the weld, the atoms move so rapidly that the state of the metal changes. This is a light microscope image of a weld. The lower piece of metal melted, and then the upper piece of metal was pushed down into it. At very high temperatures, the atoms of metal have so much kinetic energy that the solid metal melts. Further away from the source of heat, the metal cools down and solidifies. Where did the hotness in the hot spot go? The atoms in the hot spot have a lot of kinetic energy. As they rush about, some of their energy is transferred to the slower atoms in the cooler surrounding metal. As that energy spreads, temperature differences in the metal tend to even out. In fact, all energy tends to spread out and become less concentrated. This is called energy transfer. As the welder applies the flame to the metal, energy concentrated in the flame transfers to the metal and does useful work. Unfortunately, whenever heat is transferred, some of it is transferred to the environment and becomes so dilute that it can no longer do useful work. This is called lost heat. In many situations, it's important to control the amount of heat transfer and the amount of heat loss. Often, the designer and the engineer try to reduce both. Why should that be? Can you think of any examples? Here's the 840 to Peterborough. Switch to thermography. The hot areas are light, the cold areas are dark. The engine looks hot as you'd expect, but look at the wheels. They are literally glowing with heat where they run on a steel track. Why are they so hot? Where any two surfaces rub together, friction causes heating. Some of the kinetic energy that would have performed useful work is being transferred to the wheels, causing them to become hot. That heat is lost into the cooler surroundings. The thermographic camera detects it as it radiates from the wheels into the air. It takes energy to do any kind of work, such as drilling a hole. Now watch this. Heat is being generated and then lost into the environment. That means there's less energy available to do useful work, so the drill's efficiency, like the trains, is reduced. Could we improve efficiency by reducing the amount of heat being generated? How would you reduce it? Look at those piston rods. Removing metal surfaces seems smooth enough, but magnified 10,000 times, you can see how rough they really are. Oil forms a film over the surface of the moving parts and keeps them apart. The friction and the heating is reduced, and mechanical efficiency is improved. Take one cube of titanium metal, drive it towards another cube of titanium. We'll start it vibrating at a high frequency. What happens when the two pieces of metal meet? At the point of contact, kinetic energy is transferred to the atoms in the metal, so that the temperature of the metal rises until it melts, creating a weld. Friction and heat transfer can be very useful. But heat transfer doesn't only occur with friction. The electricity that drives the friction welder comes from an electrical substation many miles away. What do you think happens when energy is transferred as electricity? High voltage transmission lines. Switch to thermography. You can see that the live lines on the right are hotter than the unused lines on the left. Energy is transferring from the hot live lines into the cooler air and is lost. High voltage electricity is dangerous to work with, so the high voltage is transformed to a low voltage by transformers, like this one. And, just as you'd expect, some of the incoming energy is causing the transformer to get hot. Less than 0.5% of the energy is causing heating. But that's enough to cause serious damage, unless the engineers can get rid of it. How do they do that? Heat is generated in the transformer's iron core and copper winding. To carry the heat away, the engineers place the transformer in a container of oil. Heat travels into the oil, and then to an outside surface where it's lost into the air. How would you increase the rate of heat loss? In large transformers, heat loss is increased by increasing the surface area with cooling pipes and using pumps to increase the flow through the cooling circuits. In very large transformers, fans blow cool air across the cooling pipes. The engineers went to a lot of trouble to increase the rate of heat loss. But what about the enormous amounts of heat loss that take place at power stations, where the electricity is generated? Although modern power stations are efficient, quite large amounts of energy are generating heat which is transferred to the environment and lost. Here, the engineers do their best to reduce heat loss. Where does the heat loss take place? This is one of the main boilers. Powdered coal is blown into the boiler and burned at up to 700 degrees Celsius. The potential energy in the coal is transferred as heat to the water in the pipes which line the walls of the boiler, increasing the kinetic energy of the water molecules to produce steam. Now we're inside one of the boilers, which has been shut down for maintenance. Each boiler is as tall as a 6-story building. The kinetic energy in the steam drives the turbines and the generators, where it is finally transferred as electricity. The exhausted steam is cooled down to water in the condensers and returned to the boilers. We'll get a better view of the power station from above, and to see where energy is being lost as heat into the environment, we'll change over to the thermal camera. The smoke from the chimneys looks hot, but there's a little heat escaping from the top of these cooling towers too. It's not smoke, so what is it? Here's a diagram of the cooling circuits. When the exhausted steam leaves the turbines, it must be cooled down to water before it can be pumped back to the boilers. This is done in the condensers, where heat transfers from the steam in the boiler circuit to cold water in the cooling circuits, raising its temperature. If the water in the cooling circuits gets too hot, it won't cool very effectively. So how can heat be lost from the cooling circuits? The water is pumped into these enormous towers and is air-cooled before it returns to the condensers. The cooling towers are designed to transfer unwanted heat from the cooling circuits into the environment. Here's another power station, near London this time. Notice any difference? No cooling towers. If you wanted to use the environment as a heat sink, somewhere to get rid of unwanted heat, how would you do it? No need for cooling towers when you can draw cool water from the Thames and pump the warmer water straight back into it. You can see the warm water forming a plume downstream from the outlet in the river, cooling as it becomes more dilute. Pouring heat into the environment is sometimes called thermopollution. What do you think it's doing to the local plants and animals? Certain water plants and some animals, such as these caddisfly larvae, thrive in the warmer water. Mayfly nymphs increase their numbers dramatically. So do the leeches. Most species of fish, such as trout, decrease in numbers in the warm water, but grow more rapidly than normal in the cooler areas downstream. At the warm water outlet, the highest temperature is red, cooling to brown, and then to purple. Why should the different species be distributed in this way? Could the waste heat from power stations be used for anything? Some power stations sell their waste hot water to local homes and factories. And what happens to it there? We'll use a different kind of thermography to show that in these hot water pipes, heat is lost into the air. Flowing from left to right, the water gradually gets cooler. The top pipe contains the same hot water, so why should it look so different? It's insulated. The surface is cooler because the insulation has reduced the rate of heat loss. And because the pipe gives off less heat, its contents